Now in this video we are going to perform the second electrical experiment, and that experiment is we want to determine the specific resistance of a given wire, and as per the definition the specific resistance of a wire is the resistance of the sample having unit cross sectional area and unit length. So obviously the wire which is provided, it is not having unit cross sectional area as well as it is not having unit length, and we even cannot use that type of sample for determination of specific resistance, and that's why we will like to find the resistance of the wire with the help of Carey-Foster bridge, and we will try to determine the area of cross section of the wire and the length of the wire, and on knowledge of all these three we will be able to calculate the specific resistance of a given material of the wire. Obviously the specific resistance is not the property of a resistance or a resistor wire or a conductor, it is the property of the material. So it is independent of the length or cross sectional area, whereas the resistance depends on the length as well as cross sectional area. Specific resistance is independent. So let us start how to perform this experiment. Now let us see the experimental setup and the parts which are needed, that is the instruments which are needed. This one which you see is basically a bridge, Carey-Foster bridge. This bridge acts on the principle of Wheatstone bridge. This bridge is having a wire of length of 1 meter or 100 centimeter. This is the wire. This acts as the two resistances of the Wheatstone bridge. Then there are 4 gaps in this Carey-Foster bridge. This is the right gap. This one is the right gap. This is the left gap. You can see it is the left gap. And at the center there are 2 gaps. And with the help of this we can connect galvanometer as well as the source with all other components of the Wheatstone bridge. So this is the bridge. This you can see is a galvanometer, a DC moving coil galvanometer having a positive terminal denoted by red color and a negative terminal denoted by black color. Then we are having one-way switch for switching on or off the supply. Then we are having this rheostat. Wearing this we can adjust the null point at the center of the bridge wire. Now this is the standard cell having a standard potential of say 1.5 volt. It is known as Leclanché cell. Actually Leclanché cell is a chemical cell, but we are not using that chemical cell. Instead we are using the electronic equivalent of the Leclanché cell. This is a sophisticated circuit which provides exactly 1.5 volt whatever be the input supply. Then we are having this decade resistance box. In this resistance box, when you see, you are observing 2 dials, one dial and second dial. Can you see here in this dial it is written multiplied by 0.1 and here it is written multiplied by 1. Means whatever point you choose here, suppose we choose 1, then actual resistance is 1 multiplied by 0.1, that is 0.1. When we select second, means 2 multiplied by 0.1, which means 2.2. We are not using it, otherwise if we have used it, suppose we put this at 2, this means 2 multiplied by 1, that is equal to 2 ohms. Except all this, we are having one more thing, that is a copper strip. This strip is very thick, having very large area. It is so because we want that its resistance should be very near to 0. Although it is not possible to have 0 resistance, but it should be very near to 0. Then we are having one experimental wire the wire, the specific resistance of which is to be determined. This is that specific wire. It is cut in a length of say 15 centimeter, and there is a jockey for finding the balancing length in the bridge wire. Now see how the circuit diagram is to be made. Here is the circuit diagram for this specific experiment, where we want to find the specific resistance of the material of the given wire. This portion is the bridge portion. This is the left gap. This one is left gap. This is the right gap. And these are two central gaps. What we see is, at the right gap there is one resistance box connected. So let me connect the resistance box at the right gap. So this is my resistance box, decade resistance box. This is the decade resistance box, and I want to connect it to the left gap. So one terminal, because resistance is having no polarity, so there is no need to look for where to attach the negative terminal, where to attach the positive terminal. There is no need to bother about it, because it is a non-polar device. So the resistance is connected at the left gap, you can see it. Now at the right gap there is a copper strip connected. So let me get the right gap connected with the copper strip. This is the copper strip. I am connecting the copper strip at the right gap. So these two connections are over. Left gap connected with resistance box, right gap connected with the copper strip. Now here I see a standard cell providing a potential or EMF equal to E. The positive terminal of this is connected to the left side central gap, and at the same time with the same terminal one extreme terminal of the rheostat is also connected. So this is the one extreme end of the rheostat, and I connect the positive terminal of the supply, and both these are connected. The positive terminal as well as the extreme gap is connected to the left side central gap. One terminal of the left side central gap, it is connected here. Okay, this connection is over. Now the negative terminal of the supply is through key is connected to right side central gap, and at the same time the second extreme terminal of the rheostat is also connected. So second extreme of the terminal and one portion of the key, these two are going to come to the right side central gap terminal. So I take the second extreme terminal of the rheostat and one end of the key, and I connect it with the right side gap extreme terminal. So these two are connected. Now the second end of the key will be going to the negative terminal of the supply. So this is the second end of the terminal, that is switch. It goes to the negative terminal of the supply. This is the supply, power supply for this specific experiment, and it is getting connected to the negative terminal. Okay, this is the plug. Whenever I want to switch on the source, I will be using this plug. Now the varying terminal of the rheostat is going to come to the second point of the right middle gap. The variable terminal is going to come to the right side central gap next terminal, and the central terminal is going to go to the galvanometer, and from galvanometer is going to go to the jockey. So let me connect the variable terminal of the rheostat with the right side gap, the left terminal. So this is the variable terminal of the rheostat. This variable terminal is getting connected to the central right side gap. The one terminal which was left, it is connected to that. Now the galvanometer, this is the galvanometer, and one end of the galvanometer is connected to the jockey. You can see one end of the terminal connected to jockey. This end should be connected to the central terminal. So this end is getting connected to the central terminal of this carry capacitor bridge. Now the connection is over. I am having this jockey. So this is the arrangement for first calibrating the potentiometer wire. Means we want to find that what is the resistance per unit length of this potentiometer wire. So first we have to calibrate this wire itself, this potentiometer wire. What is the resistance corresponding to 1 unit length of this resistance wire? Then we are going to get the resistance of the experimental wire. And for that, in the left gap there is a resistance box. In the right gap there is a copper strip. As I told you, this copper strip is going to have resistance approximately equal to 0. Now the first step is, first of all, we keep the value of resistance in the resistance box to be equal to 0. This dot, white dot, is corresponding to the 0 mark. 0 multiplied by 0.1, which is equal to 0. So this is 0, this is also approximately 0. Now what we do, we switch on the circuit by switching on this Lagrange cell and switching on this and putting this key plug inside the key, one-way key, to switch on the circuit. Now the first thing is, what we have to do is, we have to keep the jockey at 50 centimeter mark. This is 50 centimeter mark. I have to keep my jockey at 50 centimeter mark, and keeping this, I have to bring the galvanometer reading to 0. You can see by varying the rheostat, I am able to vary the galvanometer's position. So I have kept the jockey exactly at the center of the wire, and see by varying the rheostat, I have brought the galvanometer reading to 0. This is the first adjustment, and this is the adjustment which you have to do only first time. Next time you are never going to change the position of the rheostat. The rheostat is now fixed. It is never going to change throughout the experiment. Now what do we do? After this, we apply a definite resistance of say 0.1 ohm with the help of this RB resistance box. Initially it was at 0. Now I have kept this resistance, across these two terminal there is a resistance appearing, and the value of the resistance is 0.1 ohm. Now when I have kept 0.1 ohm, then I have to find what will be the position of the null point. You can see, if I am keeping the jockey towards right side end, the deflection is in the right hand side. If I keep it towards the left hand end, the deflection is towards left hand. So in between this, there will be a point where I am going to get null deflection. I am lifting up the jockey and putting on the wire. I am not sliding it on the wire to find the position of the null point. You can see this is the position of the null point. Here I am going to get deflection. Here also I am going to get deflection. But see, this is the point. At this point there is no deflection. So this is the reading for 0.1 ohm. I put the scale and I find it is approximately equal to, it is 50. It is say 50.5. It is 50.5. The reading is 50.5. At 50.5 I have got the null deflection. Now I change this to keep it at 2, that is 2 multiplied by 0.1, means across these two, this left gap, the resistance appearing is of 0.2 ohms. Now again I try to find the null point, and I am using the same method for getting the null point. I am tapping the key and I am slowly moving either away or towards the null point, and you can see this is the position of the null point. Again I keep the scale. This is the position of the null point. It is around 48.8. Now it is 48.8. So gradually I go on varying the resistance from 0.1 ohm to 1 ohm, and for every reading I am going to get the position of null point, and I am going to mention this reading in the place where it is written that the position of null point when the resistance box is in the left side. So that will be the first part. Now I am going to interchange the position of the copper strip and the resistance box. Means now resistance box will be shifted towards the right side gap, and this copper strip will be shifted towards the left hand side gap. And after that again we are going to take the reading. As I told you, now I have brought this decayed resistance box in the right gap, and I have taken this copper strip to the left side gap. So now again I am going to repeat the same thing. I am going to produce a resistance of say 0.1 ohm on the resistance box. Again I am going to find the null point. As you can see, in this side the deflection is in the left hand side. This side the deflection is towards right hand side. So in between these two I must get a position of null point. So I am trying, see how slowly I am lifting the jockey and putting it again on the wire, because if I slide this jockey on the wire, obviously the wire's temperature is going to change, and because of that the property of this wire is going to change. See, this is the position of the null point. I am putting the jockey, still there is no deflection. So I take the scale, put it here, and I find the reading is 57.5. Similarly, I increase the resistance to 0.2, and again I try to find the null point, and you can see I am getting null point here, somewhere here. See, this is the null point, and the null point comes around at 59.5. So by doing so, again I start taking reading for 0.3 ohm, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1 ohm. So that will be the complete process for determination of the resistance per unit length of this specific bridge wire. Just one thing you should be very careful about is that whenever you are writing the readings on the observation table, if the resistance box is in the left side, then write the readings in the place, in the column which is marked as the position of null point when the resistance box is in the left gap, and keep the readings in the column when the decayed resistance box in the right gap, where it is written that position of the null point when the resistance box is in the right gap. So be very careful about it. Now the last thing remains, and the last thing is I want to find the diameter of the experimental wire. I have been provided the wire of a specific length, and that length is 15 centimeter, and it is given, it is provided, so I need not measure it, but the diameter of the wire is not provided, so that diameter is to be calculated. Now to take the diameter, basically we want radius, but the radius will be obtained if we know the diameter of the wire. So for finding the diameter of the wire, you can see I have put the wire in between the two jaws of this screw gauge, and I have taken the reading. While I take the reading, you can see the main scale reading is not 1 mm, instead it is equal to 0.5 mm. The 0.5 mark has been crossed. The 0.5 mark has been crossed in the main scale, and if you see the circular scale or a head scale of the screw gauge, you can find the 15th mark has been crossed, 16th has been crossed, but not 17. So 16 will be the head scale reading. So 0.5 centimeter, sorry 0.5 millimeter or 0.05 centimeter is the main scale reading, and 15th division multiplied by 0.001 is the in centimeter is the reading of the head scale. How to get the least count, how to find the zero error, all this we have already talked in another videos, so we need not repeat it here. So 0.5 mm is the main scale reading, and 15 multiplied by 0.001 is the head scale reading. Okay. Now see the reading for the first table, in which we want to find the resistance per unit length of the bridge wire. The reading is like this. In the first column, we are writing the resistance which appears in the resistance box in ohms. So as I told you, it is 0.1, 0.2, 0.3, 0.4, 0.5, so on up to 1 ohm. Now this is the position of the null point when the resistance box in the left gap and resistance box in the right gap. So when it is in the left gap, we are taking L1. When the resistance box is in the right gap, we are taking L2. So by varying the resistance, keeping the resistance box in the left gap, we have taken reading. For 0.1 it was 49, 0.2 48.6, 0.3 48.2, 0.4 47.2, and so on. When I interchange the position of the resistance box and the copper strip, then the resistance box came in the right gap. So for same 0.1 I have taken the reading 57.4, for 0.2 59, for 0.3 it is 60.5, 0.4 it is 61.8, and so on. Now in the next column I am having the difference of L2 minus L1. Mind it, for resistance per unit length of the bridge wire, this gap, this difference between L2 minus L1 is always positive and goes on increasing with the increase in the resistance appearing in the resistance box. Now we get the value of the resistance per unit length for each reading, and resistance per unit length is basically equal to X, that is the resistance appearing in the resistance box, divided by this L2 minus L1, that is 8.2. So it is 0.1 divided by 8.2, which comes to be equal to 0.0122. For 0.2 I have taken the same calculation. It gives the value of S to be equal to 0.0192. For third, that is 0.3 ohm, it is 0.0244, 0.0274, 0.0281, 0.0294, and so on. Now I take the mean of all these readings, and that is mean S, that is resistance per unit length, that is ohms per centimeter, which is equal to 0.0266. For the second set of reading, that is for determining the resistance of the experimental wire, as I told you, we have replaced the copper strip by the experimental wire, and we are doing the same experiment with the same method. Now again I have put the resistance in the resistance box to be equal to 0.1 ohm. I am finding the null point with resistance box in the left gap with the experimental wire. It came to be 63.1. For 0.2 ohm it is 61.8, 0.3 it is 60.9, and so on up to 1 ohm. Similarly, by interchanging the experimental wire and the resistance box, when the resistance box comes to the right gap, Again I try to find the null point, and this time the null point for 0.1 ohm is 46, 0.2 ohm it is 47.6, 0.3 ohm it is 49.7, 0.4 51.5, and so on. I go on doing it until I reach 1 ohm resistance. Again I try to find the difference between L2 and L1, that is L2 minus L1, means null point when the resistance box is in the right gap minus the null point where I got the null point when the resistance box was in the left gap. So 46 minus 63.1, obviously it comes to be negative, that is negative 17.1, it is negative 14.2, it goes on decreasing up to negative 2.1, then it becomes positive. So in the case of first table, all the readings were positive. In the second table, the few readings, initial readings, are giving negative value of L2 minus L1, and for others it is giving positive. So it is not a mistake, it should be like that. Now with the help of this, I try to find the R, that is resistance of the experimental wire, which is X, that means this X, minus S which we have calculated the mean value of the resistance per unit length of the wire, multiplied by L2 minus L1, this. So the value of resistance comes to be 0.5546. For the second reading it 0.5775. For third reading it is 0.5977, and so on. For each reading I go on calculating the value of the resistance, and ultimately I take the mean of this, and the mean comes to be equal to 0.6508. This is the mean value of R. Now we have got R. If we know the resistance, the length of the wire, length of the experimental wire, and the diameter, that is area of cross section of the experimental wire, we will be able to calculate the specific resistance. So let us see the value of the diameter. So let us see the table for obtaining the resistance, the diameter of the experimental wire. Now this is the reading of diameter of the wire. The main scale reading was 0.5 mm, which is equal to 0.05 centimeter. The division on the head scale was equal to 5. So it is 5 multiplied by 0.001, which comes to be 0.005. This 0.005 added with this gives us the value of 0.055. This is the diameter along any direction. Now we rotate the screw gauge so that this time we are measuring the diameter along perpendicular direction, and again the main scale reading is 0.05 centimeter. The head scale now division is 8, so it is 0.008. The total reading becomes equal to 0.058. Now I have the two diameters, one along any direction, second is along perpendicular direction. I add these two and divide it by 2 to get the mean diameter. Mean diameter comes to be equal to 0.057. Dividing this diameter by 2, I get the mean radius, which is equal to 0.028 centimeters. Now we come to the last part of the calculation. For calculating the specific resistance rho, the formula of rho is, it is equal to R, that is the resistance of the wire, multiplied by pi r square, that is the area of cross section of the wire, divided by L, length of the wire. So we are having the value of R, we are having the value of L, we are having the value of R. So obviously we can calculate rho. So let us put the value. I have put the value of R, which comes to be equal to 0.6508, multiplied by the value of pi, that is 3.14, multiplied by a square of 0.028 divided by 15. The numerator comes to be equal to 1.602 into 10 raised to minus 3 divided by 15, gives us the final value of 1.068 into 10 raised to minus 4 ohm centimeter, or if I convert it into meters, it is 1.068 into 10 raised to minus 6 ohm meter. So that's all in this experiment. We have done each and every part, if we have calculated and you have got the final value which was to be calculated, then our experiment is over. If we get the reading and do not calculate, our experiment is incomplete. So please go up to the aim. The aim was to find the specific resistance of the given material of the resistive wire. So we have come up to the point where we have got the value of rho, that is specific resistance, which comes to be equal to 1.068 into 10⁻⁻⁴. That's all in this experiment.